So here we go with the Chapter 4 review questions. Going to go ahead and work through the solution methods for all of the ones that require calculations, and then just give you a little bit of an explanation for the ones that are conceptual. Now the first one we have here is number 59. This is the one where you are told that you're going to travel 15 meters. You're then going to turn 90 degrees, travel another 22, turn 90 degrees, and travel another 5. Now it doesn't tell you which way you are turning the 90 degrees. So what that means is there are 4 possible locations where you end up being. And it asks you, what is the displacement to those 4 possible locations, and which direction are you going? So we need to figure out the distance from our starting location to A, B, C, and D, and the angle that we would need to orient ourselves in. Now what angle are we going to compare everything to? Well, we're going to compare to the vertical here, right? We can get a straight line on that one. We're comparing from this 15. We want to compare it to that, right? So we need to measure over from there. Now how do we get those distance measurements? Well, if you notice, we have that mirror image going on. The left-hand side and the right-hand side are exactly the same. So what we can do is if we solve for A, we know the answer for C. If we solve for B, we know the answer to D. The only difference is whatever angle we find that we need to face to the left to get to A, we have to reverse that, and that angle now needs to be faced to the right to get to C. Same thing for B and D. So what I want to do is draw in some triangles that we're going to utilize to figure out these distances, and then explain how we're going to utilize those triangles. Alright, so the 2 triangles I drew in there are for B and C. Now you would also have, technically 4 of those. You would have one that is from the start to A, which would have a side along here and a side along the bottom, and one to D, which would have a side here and along the bottom. But I don't want to cluster up the diagram, so I drew the triangle on the right-hand side to C, and that will represent the same thing for A, and then the one here for B will represent the one for D as well. Now once those triangles are drawn in there, you'll notice that we have an adjacent side and we have an opposite side for each of those. And the distance from our starting location to the point is going to be our hypotenuse. So what that allows us to do in order to find that displacement, that distance from start to location, is use the Pythagorean theorem. And to eventually get the angle, we can use an inverse trig function. So for, let's say, we'll start off with B. That triangle, our opposite side, is going to be 10. And the reason it's 10 is because if we went up 15 and we ended up coming back 5, then from that position to where we started, this vertical measurement here is going to be 10 meters. Now, the adjacent side, since we just went to 22 to the left, that adjacent side is going to stay the value of 22. So let's go with c squared being our hypotenuse. This equals 10 squared plus 22 squared. And then we'll want to solve this through for c. So there's our answer for the displacement to get to point B. This hypotenuse length here is 24.2 meters. Now we need the angle in which we need to orient ourselves to get there. So we're going to go ahead and use the tan function. So we go theta equals inverse tan of opposite over adjacent. Now what we need to do is we need to actually flip our values here. Because if we were trying to figure out the angle from which way we started off being oriented, right? If we're using the sides opposite and adjacent, these 2 values here, the angle we're finding is this one. So the ways you can get these are, you can either take 90 degrees, because that's the kind of angle you have here, and subtract what we get using our values 10 and 22, as 10 on top, 22 on the bottom. Or we could also draw our triangle the other way. If we had to shift this green line up and drew our triangle upside down here, the opposite side now would be our 22 and our adjacent side would be 10. So we can either just flip these and do inverse tangent to go straight to this angle, or we can do inverse tan with them in our normal setup and then subtract that value from 90 in order to get that angle. Either way is viable. I'm going to be getting 65.6 degrees. So our answer right now for B is 24.2 meters at 65.6 degrees, and I would add to that either left or west. Now, if B and D are mirror images, D would be the same thing. The displacement equals 24.2, and that is 65.6 degrees right, or east, depending on how you want to write that. So by solving for 1, we've already solved for 2. Now let's go ahead and do C, and that'll also be our answer for A. Now for C, we need to identify our values for these opposite and adjacents. So our adjacent side here is still going to be 22. But our opposite side is now going to be different. If we went up 15, came over, and then turned and went up an additional 5, then this side is going to be 20. And I'm getting 29.7, not degrees, meters for that. So that's going to be how far it is from start to the location C. We need to get an angle on that one as well. We can do that the same way, the inverse tan function. And again, your choice as to which one you make, opposite or adjacent. I'm going to do it so that 22 is on the top and make that my opposite side here. So we're orienting the triangle upside down compared to how it's drawn there. If you do it 20 over 22, make sure you take that and subtract that from 90. So we have the answer for C then. We have that 29.7 meters at an angle of 47.7 degrees, and that's going to be east or right. And therefore we also have A, but A we would answer as 29.7 meters at an angle of 47.7 degrees west or left. Alright, so there is your work through for number 59. So check back in for the next one. Alright, so we have 69, 71, and 78. All three of those are conceptual problems, so there's really no need for calculation. Now for the first one, 69, it's asking, say you're running through the rain with an umbrella, how should you angle your umbrella in order to minimize how wet you're going to get? So if you are running, right, relative to the rain, what's going to happen is the rain essentially is going to be falling towards you at like an angle, as diagrammed there. Even if it's falling straight down, it's going to be coming at you as you're going towards it. You're basically running into the droplets. So if we looked at rain droplets in locations A, B, and C, droplets A are going to be falling behind you. B, droplets directly above are going to be ones that are hitting at the top, but they're really coming from the top right. And then C is going to be missing the front of the umbrella, but as you're running into droplet C. So it may miss the front of the umbrella, but the bottom part of you is still going to be getting caught by that. So how do we want to orient the umbrella? We should be tilting it forward slightly, and that is so that the droplets that are directly above you, although they may miss the back of the side of the umbrella, since you're running, they're going to be still falling behind you. You're going to catch all the droplets that are falling in front of you, and catching the ones that would have been missed by the umbrella in the first place, and then would have hit you like lower down. Now it's going to be getting caught by it. If you want to think about this in terms of, like, say you're not running, but just think of rain that is falling at an angle, you don't still hold your umbrella straight up. You turn your umbrella to face the rain as it's coming at you. So if you have real heavy winds, you'll always point your umbrella into the wind a little bit, so that way you're not getting rained on the one side of your body and then totally dry on the left-hand side. That way you can keep yourself covered for the most part. Now for 71, we have two planes, one of which is refueling from the other one. So plane B is being refueled by A. You're told that plane A is traveling at 125 kilometers an hour. That's how fast it's flying. We're asked two questions. What is the relative velocity of plane B related to A and related to the ground? So if plane A is traveling at 125 kilometers an hour and B is refueling it, it's actually connected to plane A when they're refueling, then plane B has to be traveling at the same speed as A. So relative to the ground, plane B is traveling at 125 kilometers an hour, just like plane A is. Now relative to plane A though, if plane B is traveling at the same speed, then relatively speaking, it is traveling at 0 kilometers an hour. Think of it like two people driving down the interstate. You're traveling at 70 some miles an hour, but the person next to you in the car is traveling at 0. You're both traveling at 70 relative to the ground, but relative to one another, you're traveling at 0. Now 78. 78 gives you the initial components to an object's or a projectile's velocity. It gives you the Vx component 5 meters per second and the Vi component of 6. Now that Vi is the Viy component. Keep that in mind. Because what it's asking is, what are the components of the velocity at the very top of the arc? What is Vx? What is Vy? Now we know that in projectile motion, Vx is unaffected by anything. There's no gravity acting on in the x direction. Gravity acts vertically. So x should stay constant. So if it's 5 meters per second, it'll be 5 meters per second everywhere within its path. So at the very peak, Vx is 5. Viy, however, is affected by gravity, so Viy is going to fluctuate. If it starts off at 6, it's going to be decelerated on the way up. It's going to be accelerated on the way back down. And it's going to be going up at positive 6. It's going to end up coming back down at negative 6. So at some point in time, we have to make a transition from positive to negative values. So we have to make that transition through 0. It's going to be shot upward at 6 meters per second. It's going to decelerate to 0 when it gets to the peak. And then it's going to accelerate back down to negative 6 meters per second at the bottom. Okay? So there's 69, 71, 78, the explanations. On to the next couple. Okay, so this next set is going to be 79, 80, 81, and 82. So for the first one, 79, it has a child that is eating an ice cream cone while riding a horse. Unfortunately, the ice cream falls out of the cone, and it asks, what does the child see from their perspective in terms of what does the cone look like it's doing, and what does a parent standing off to the side see? Well, according to the child, we're going to think about this in terms of like relative motion. Now, the child, the horse, the ice cream cone are all moving forward together at the same speed. same velocity. As the cone leaves, or the ice cream leaves the cone, it's going to have the same velocity that it had when it was connected to the cone. So according to the kid, it's going to look like the cone and the ice cream itself falling out of it is moving along with them. So to them, it's going to look like it drops straight down. Think of that in terms of, say, you're walking and tossing something up and down in the air. It has that same forward velocity that you do. So when you toss it up, it comes back down into your hand. It actually has a forward velocity to it. You are not throwing it forward in order to catch it. You're throwing it straight up. But since it's moving with you, it has that forward velocity. That's what's going on with the cone and going on with the ice cream. Now to a parent off to the side though, they're going to see that the ice cream leaves the cone, has that forward motion, so in terms of their path that they see the second half of a parabola. They're going to see what's drawn there. It's going to moving forward and falling. Now 80 is asking what is the acceleration when a projectile reaches its highest point, what is just before and just after this highest point. Now there's a common misconception here. When a projectile is in the air, there's a misconception at the peak when it hits a zero velocity that it has an acceleration of 0. Now the issue with that is, remember, acceleration is the change in an object's velocity. So if the acceleration hits 0 at the peak, then the velocity doesn't change. If velocity is not changing, then it's going to stay where it is. It's going to hover. So we know that's not the case. We know that there's no point in an object's flight at which it hovers. It may appear to, but it's either going up or it's coming back down. So what is the acceleration at the peak? Well, it's the same as it is everywhere else. It's negative 9.81 meters per second squared. It's the same as gravity before, after, during, all motions, all points. It's the same. That's answer to that question is going to be then what is the acceleration? Negative 9.81 at the peak, before the peak, after the peak, everywhere. All right. Now 81 is looking at 3 different trajectories and it's asking us to rank in an increasing fashion the initial speed or initial velocity at which they were launched at and the time of flight. You'll notice with A, B, and C, they all go to the same height. They all go different distances, and they're obviously launched at different angles. So let's first look at the time, how much time they spend in the air. Now, time is related to the vertical component of the projectile's motion. Right? How fast it's launched upward and how high it goes. Since gravity is affecting everything the same, right? If they all get launched to the same height, it's going to take gravity the same amount of time to slow it down on the way up, same amount of time to speed it up on the way back down. So what that tells us is that vertically speaking, they were all launched with the same VIY, the same initial vertical velocity. So in terms of times of flight, it's identical. A, B, and C all spend the same amount of time in the air. So if they all spend the same amount of time in the air, because they all go to that same height, right? You could also think of that in terms of going back to our bullet drop thing. You drop a bullet from a certain height and you fire a bullet from a gun at the same height. They have different horizontal velocities, so they go different distances horizontally, but they both fall the same distance, so they both spend the same amount of time falling. They both have the same t value. So if this were A, were say something just rolling off a table that's a meter tall. B is something being thrown from a table that's a meter tall. And C is something shot from a meter tall. They're all horizontally speaking, starting at this peak here, down, they all spend that same time. So at the same time down, same time up, we're going to say the same thing here, even though they're shot at an angle. It works out the same way. Now if we know that, we're going to work to the total velocity. If they all have the same time of flight, they all have that same VI, the same VIY. If they're all going different distances, delta x, then that means they had to have had different Vx values, different horizontal velocities, in order to go further in that same amount of time. So if A goes the shortest distance, then A had the least Vx, B had the next most, and C had the highest value for Vx. So if we look at our total velocity then, the combination of Vx and VIY, A has the least Vx with the same VIY, so it has the lowest amount of total velocity. B would then have the next highest total velocity, and C would have the highest because it traveled it traveled the furthest distance in the same amount of time as A and B. Now, make sure you have that written. These are all equivalent. So it should be A equals B equals C for the time part. Now for 82, we're looking at a situation where we're given that the initial velocity something is launched at is 12 meters per second, and that at the peak it's it launched at 12 meters per second, and the minimum velocity it hits is 6 meters per second. Well, looking at the trajectory, the minimum velocity occurs at the peak, because at the peak we know that Vy is 0. And if total velocity is a combination of y and x throughout the motion, if the combination at the top is 6, 0, that has to be our minimum location, right? Or it's something in 0. If our minimum occurs at the peak, then that means Vx has to be the 6. So if Vx is 6 and Vt is 12, we can work through our trig functions to figure out the angle it's launched at. Our hypotenuse is the 12, our Vx, our adjacent side, is 6. We can go ahead and use the inverse cosine function to get our angle, which comes out to be 60 degrees. Alright, so here we are for 83 and 84. 83 is dealing with the racquetball that is struck at 4.87 meters per second. And the thing lands 1.9 meters from where it's hit, and it's wanting us to figure out the height at which it is hit from. Okay, so the values are given are Vx, delta x. Drew a little diagram here, threw in our chart, plugged in those values, that Vx and delta x. Now, since it says it's struck horizontally, we know that Viy is also going to be 0, and acceleration is always negative 9.81. So we can fill in most of our chart here. Now the unknowns we have are the VFY, the delta y, and the t. If t is unknown and there's a way to solve for it, that is always the first thing we should do. So we go ahead and we do here with the delta x equation. We know how far the thing goes, we know what Vx is, we can plug those values in and find out time, getting a time of 0.4 seconds. Throw that in both sides of our chart. We then jump to our delta y equation to then figure out the height. We're going to use this one because this is a simple plug and chug since we know time. If we didn't know time and we wanted to figure out height, we could also have gone through our Vf squared equals Vi squared equation with that 2a delta x and solved it through that way. But plugging this values in, our 0.4 for both t's, making sure that you only square the 0.4, you end up getting a delta y of negative 0.78. Now, it asks for what is the height of the thing getting hit at, or what is the height it's getting hit at. And when we talk about heights, we generally refer to those as positive values, so we're looking at this as an absolute. The negative 0.78, that is negative because it's from the racquetball's perspective. It is dropping 0.78 meters, so that's why it's negative. But in terms of a height measurement, no, we just plugged it in as positive 0.78. Now for 84, we were given the height of, I believe, Victoria Falls, and the velocity at which the water is leaving the falls at the top, so it's Vx component. So if we were to create our chart like we did before, we would have Vx and delta y again, as well as Viy being 0 because of the fact it's leaving horizontally off the falls, and a of negative 9.81. Same process, we want to find time first, except for this time it wants us to know what is the total velocity it's hitting the ground at. So to know that total velocity, we would need to know what Vf, y, and Vx are to find the total. We normally work the other way around. We're given the totals at the beginning and we break them into components. Now we're going to work the other way. We want to find the total, so we can calculate our components, put them together to then get the total. So still, first, time. So finding time, we're going to use the delta y equation. Jumping to that one, since vi is 0, we don't have to worry about the quadratic formula, so we have negative 108 equals the 1/2 negative 981 t squared. Work through this. Make sure you were dividing this negative 4.905 over and not adding it. Take the square root, you get 4.7 seconds. The next bit, now you know the time, you can figure out what VFY is. Going to your VFY equation, this one here, you can plug in 4.7 seconds and you get a VFY of negative 46.2 meters per second. That's the vertical component of this velocity when it hits the ground, or hits the rocks or whatever at the bottom. And we were given the 3.6 was the Vx at the beginning of the problem. So since that's constant, it's still the same. So we have the two sides of a triangle here. We need to know what total is. We need to know what this Vt value is. That is the hypotenuse with these two sides. So we can go ahead and jump to the Pythagorean theorem. The Vt squared equals Vx squared plus Vy squared. That's our velocity right for the Pythagorean theorem. Plugging in our 3.6 and our 46.2, we get a total velocity of 46.3 meters per second. And that's really not a velocity because we're not giving a direction to that right now. We're just saying it's a value. If we wanted to properly write that out, we would have to do a trig function to get this angle or the angle below the horizontal, and then say our answer is 46.3 meters per second at blank degrees. But the question actually asks for speed. Speed doesn't care about the direction, so we can just go ahead and answer that as 46.3 meters per second, and we're done. So, next set of questions. Okay, so here we have number 91. So here is a golfer that's taking a swing and hitting a golf ball with an initial velocity of 34.4 meters per second at an angle of 45. Oh, it doesn't say the angle really. It says what is the maximum distance that they could make a hole-in-one. So we're making a few assumptions here. The first one is that this ball lands in the hole and doesn't bounce out. So that's how we're going to do this. We're not going to worry about any kind of rule involved here. The other one is we need to know what the maximum distance is. Well, the maximum distance occurs theoretically at 45 degrees. Now, is it actually 45 degrees? Well, that depends on the ball. It depends on the type of the ball, it depends on its design, it depends on the spin it has. A lot of things factor in to what exactly is the most efficient angle for that particular projectile. But from a theoretical sense, neglecting air resistance, which throws a lot of that out the window, it's 45. So we're going to make our angle 45. We're going to keep our V total as 34.4. Our diagram is provided. We have our values. Now, since we have V total and theta, that doesn't go anywhere in the chart. The first thing we need to do is break that V total into its components. We need to have the Vx component and the Vy component. So to get Vx, we're going to do the Vt cosine function. To get Vy, we're going to do the Vt sine function. You'll notice that both values come out to be the same, 24.3, and that's because the angle is 45. And a 45-45-90 triangle, like what we have here, the two sides of the triangle are identical. So a quick check on your problems in future references is if you have an angle greater than 45, your y component, the height of that triangle, should be greater than the length, the x component. If the angle is less than 45, the y component should be less than the x component. And if it's the same, if it's 45, that means that should be the same. So here we have our two components. We can go ahead and plug those into our charts, there and there. And if it's being launched upward of 24.3, we know it's going to come back down to negative 24.3, so we can plug that in for VFY. And that is because it's coming back down to the same height it was hit from. It'll sit off the ground, it's going to come back down to the ground. We know those two values are the same. A is always a given. And looking at our chart, we don't know delta x, we don't know delta y, we don't know t. As always, t is the first thing we need to find. So we use this equation, the VFY equals the VIY plus AT, plug in our values that are given, and we solve through and get a total flight time of 5 seconds. That's from the moment it gets hit to the moment it lands. Now the question is, what is the maximum range? So at this point in time, we've got everything but delta x and delta y. We only care about the range, so we don't really care about how high the ball goes. So we're not going to worry about solving for delta y. We're just going to go straight to delta x. So to find delta x, we use the delta x equals vxt equation and plug in our 24, 3, and our 5, get 121.5 meters as the total distance, or the furthest possible shot that they can make. The next bit is asks, what is the minimum speed? Where does it occur at? And we know that at the beginning we have a combination of Vx and Vy. At the end we have a combination of Vx and Vy. We have the same going on everywhere in between, except for at the peak. Because at the peak, we know that Vy equals 0. So the entire velocity is only dependent upon the x component. So 24.3. So where does the minimum occur? It occurs at the peak. What is it? 24.3 meters per second. All right? On 92. And here we are for number 92. 92 is the one where we're talking about a football being punted, and we're asked about the initial speed at which it was kicked at. So we're assuming it's kicked and lands at the same height. It's kind of an approximation again. We only know that the angle it is kicked at is 63 degrees, and the total hang time of it is 4.5 seconds. So with that information, how do we get around to what VT is? Okay, so let's see what we can find with that. If we know what the time is, 4.5 seconds from when it gets kicked to when it lands, so 4.5 seconds from one all the way to the other, we know that to the peak is going to be half of that time, so 2.25 seconds is how long it takes to go up, and it takes an additional 2.25 to come back down, which is stated over here. And we know that we can solve this either the upward motion or the downward motion, so we're going to do this the upward motion first. We know it hits 0 at the top. We're going to solve for VIY. This is the one we're going to try and figure out. We're going to plug in a time of 2.25, and we get that the initial vertical velocity is 22.1 meters per second. So that gives us what VIY is, and that also technically gives us VFY. If we wanted to write that one in, we could say that's negative 22.1. Now from here, there's a couple things we could do. The easiest route is what's shown down here, and that is looking at our VIY equation. We know one side of our triangle here. We know the VIY component. We're looking for the VT component. So VIY is the opposite side of our starting triangle, right? So if VT is the velocity it's kicked at, we know we have the horizontal component and the vertical component. We have this being 22.1, and we have this angle here being 63 degrees. So we can just go to a trig function to find out VT. We don't need to figure out delta y, we don't need to figure out Vx, we don't need to know how to figure out how far the thing goes. We can jump right to the total velocity. So we're going to go ahead and do that. So VIY equals the VT sine theta. Plug in 22.1 for VIY, plug in our theta of 63 degrees, work that through, and you get an initial velocity of 24.8 meters per second as V total. And that's all we have to do for number 92. Alright, so to finish things up here, we have 94 through the 104. So it's asked for, you have two people that throw a snowball, or throw snowballs, off of a something rooftop, and one of which throws it horizontally outward, one of which throws it straight down. It asks for, once they're in flight, how do their accelerations compare? Now, once they leave the person's hand, the only thing acting on them is gravity, and because of that, and that being the only force acting on it, then acceleration for both of them is negative 9.81. So the acceleration is the same, you know, once they leave their hand. I mean, in the hand, I mean, they're different because of the way they're being thrown. But as soon as it leaves the hand and they're acted upon by only gravity, they are the same exact accelerations from that moment to when they hit. Now for 96, if you're walking along and you're throwing something up into the air, and you want it to come back down in your hand, how do you want to throw it, make it land there? The answer is going to be straight upward. And it's going to be that because while you're moving forward and you have this thing in your hand, it has the same forward velocity that you do. So when you throw it into the air and give it that upward velocity, it has the forward velocity that it already possessed because of your combined motion. So it will come back down in the same spot. If you were to throw it with some forward velocity as you're walking forward, it's going to land further ahead. If you were to throw it with some kind of a backward velocity, it's obviously going to go backward. Now for 97, two divers are jumping from a cliff, running off of it horizontally. The one has twice the speed when jumping off of the cliff as the other one. So how do their landing positions compare? So then you consider here, as they're both leaving from the same height, they both have an initial vertical velocity of 0, so they're going to be in the air for the same amount of time. So t is going to be the same for both of them. And when we talk about horizontal distance, how far they go, we're looking at that delta x equals vxt equation. And if t is the same for both of them, but the vx, the velocity at which they're running off the cliff at, is double for the one, then that means it's going to double the delta x value. So if the answer for that is it should be twice as far for the one, and the reason is the drop time is the same for both divers. Now for 102 through 104, that is related to the Mars rovers and how they landed those for one of their missions, where they utilized airbags. So the questions that are, or the values that are given really, is it gives you the acceleration on Mars, so 3.72 meters per second squared, so negative 3.72. And it says that the airbags inflate from a height of 16.7 meters, so it's retrograde thrusters all the way down to that point, and then the airbags deploy. And it's asking for, well, how much time elapses between the first and second bounce from when it hits to when it hits again, how far does it travel while bouncing, and how high does it bounce up to while it's doing all of this. Some of the values that it gives us are that it bounces upward with a speed of 9.92 meters per second and at an angle of 75 degrees above the horizontal. So you'll notice that when first reading through this, I was writing down values that were necessary or that I was picking up on, and I wrote down this 16.7 meters expecting to need to calculate like how fast it's going when it falls. That ends up being irrelevant information because it gives you VT. So since we have VT and we're given the angle 75 degrees, we're going to have to find components and then go through the process that we do with every other problem. So I've got the diagram over here on the right. Also have our chart filled in with what we can at least have. And the only thing we have is acceleration, and this should be the negative 3.75. And in my calculations, I used the correct one. In the chart, I put in the wrong one. Just force of habit. So with that being the only thing we can plug in, we need to go ahead and find these components. We need to find Vx, so we need to find VIY. So 992 and cosine of 75, and then sine of 75. We get two values. That our x component for Vx is 2.6, and our y component for VIY is 9.6. Now if it goes up at 9.6, we know it's going to come back down at negative 9.6. And we're going to utilize that to figure out our time, which we do here. So plugging in our negative 9.6 or positive 9.6, we find out that the total time is 5.2 seconds. So what we're going to do is we're just going to kind of solve this through like a normal problem and then pick through A, B, and C answers. So we get a time of 5.2 seconds. And if we look at our questions, we notice that that is the answer to 102. All right. And it's multiple choice, so that means it's 102, and choice C is the closest to that answer that we have. Next bit up is we are going to go ahead and let's find delta x. So we're going to use the delta x equals vxt equation. We know our vx, we know time now. We get an answer of 13.5 meters, which is closest to 13.2, which is option A for number 103. And then the last bit, we want to know how high this thing bounces. So the delta y equation, we plug in our half time. We don't want to plug in the full 5.2 seconds because 5.2 seconds later the thing is back on the ground. We want to know the maximum height, so we want to use a t of 2.6. Plug that through, you get an answer of 12.3. That matches up with 104 exactly. So we have everything we need to know. So 102, 13, and 14 are all done.